So a rock is thrown vertically upward. So if you want a graph of the height where time is on the x-axis, the graph might look like this. Rock is going up and up and up, and it reaches its highest point, and then it starts coming back down to earth. This isn't a path of the rock, right? That's a just a graph of the height. The path of the rock is just straight up and then straight back down. That's a graph of the height depending on what time you're talking about. And there's our function that models that height. We're supposed to find the rock's velocity and acceleration as functions of time. That just means the first and second derivative. So the power rule, the 1 comes down and multiplies. The 2 comes down and multiplies. So there's the derivative. So there's a graph of its velocity. The second derivative is going to be negative 1.6. I think it's a graph. It's a function of time, and it's a function of the velocity. This is the function of the acceleration. The acceleration is constant. Okay. How long did it take the rock to reach its highest point? The highest point would be where the slope is 0, right? Where it levels off. So you want to plug in 0 in for the derivative and solve. Okay, so if you solve that equation, I don't know what I was doing before. If you solve that equation for t, you should get t equals 15. That's the highest point because that's the only place in that graph where the slope is going to hit 0, right? So take the derivative, set it equals 0, and that's how you find all potential maxes and mins other than the endpoints. How high did the rock go? This is when it reached its highest point. If we want to know something about its height, that's what S is. So we're going to plug in 15 into that equation. 24. And look, this isn't the derivative, right? We're looking for location, so we're looking to plug in 15 into the original function. What was it? 0.8? 0.8, 15 squared. Okay, so I'll do that real quick. 15 times 15 times 0.8. So that's 180. Well, that's 180 for the maximum height. When did the rock reach half its maximum height? I don't know why you'd want to know this, but if that's the maximum height, then you want to know when S is equal to 90, right? So plug 90 into the original equation. That's not really a calculus question. Plug 90 into the original equation, and now you have something to solve for t. So I'd set it equal to 0 by subtracting that 90 from both sides. So you get something like this, and I'll put it in descending powers. Okay, just set it equal to 0. I like to deal with quadratics if I can have the leading coefficient be 1 because it's a lot easier. So let's see if we can factor out that negative 0.8 from everything. Maybe it'll be yucky, maybe it won't, I don't know. So we got t squared, and now 24, I'm factoring out 0.8. I got negative 30 there. You could check me by distributing that back. It should turn back into the same thing. And then 90 divided by 0.8, that's going to be positive in the end. Oh, man, that was close. Okay, so it doesn't come out clean. It's going to have a mixed number at the end. So got to use the quadratic formula, but I'll leave that for students to do. When did it reach its maximum height? That means when did we get 90 in for S? What are the values for T? There should be two places, right? Quadratic formula gives you two places. There's half its height. So you should have two different time intervals, but use the quadratic formula to find out when it reaches its height. And how long was the rock afloat? Well, here's where it started. Here's where it ended. We're really looking for this time point, right? And the height there is 0. So all you have to do for this question is plug in 0 into the original equation and solve for t. Okay, that's factorable. Factor out the t. And then you set each factored piece equal to 0. So t equals 0, that one's common sense. The thing's on the ground when we start. 24 minus 0.8t. If we set that equal to 0 and solve, that will tell us the ending point. So 24, that's going to be divided by 0.8, so 30. It was aloft for 30 seconds, which makes sense. If this is a perfect quadratic, you should be halfway done when you reach your maximum. So it was aloft for 30 seconds. We just set this quadratic equation equal to 0, and that told us the two endpoints.